We're now moving on to the second lesson within the differentiation chapter in the Year 2 Maths textbook. So what we're going to look at today is how to differentiate exponentials and logarithms. Before we go on to that, we're just going to have a little warm up, a reminder of some work we were doing before. Always good to keep practicing those skills. So what I'd like you to do is to write down the question and then pause the video and have a go at it. Okay, so hopefully you have had a go at it. Remember, when you're solving trig equations, always have a look at whether we're talking radians or degrees. You can tell by the range of values there that we're talking radians. Now, the key is really with solving trig equations, you can get such a wide variety of them. So you've got to be able to look at it and kind of think, well, what am I going to do with that? Now, the two trig parts of it are both sine 2x. So hopefully you're thinking, okay, well, I need to gather together the sine 2x's. So what I'm going to do first then, hopefully this is what you thought to do, is to multiply through by the denominator. Okay, so I've got rid of my fractions, which is commonly something that you want to do really when you're solving any sorts of equations, is getting rid of fractions. I'm going to gather all of the sine 2x's on one side. Okay, I've got 4, have I? I've got 2 and 1, which makes 3. So sine 2x's on one side, numbers on the other. 2 minus 0.5 gives me 1.5. So I end up with the equation I'm solving is sine 2x equals 1.25 over 3, which is a half. Okay, so I'm now on to using my calculator. I'm going to use my sine to the minus 1 function, but remember with Excel they like you to say arc sine. Pop that in my calculator, make sure you're in radians mode. This is one of your common angles, so that gives you pi by 6. We need some more answers, so let's draw a very wiggly cast diagram there. It's a bit of an angle, but never mind. So this is my pi by 6. It's sine and it's positive because it's equal to half. So I'm also going to be in this quadrant. Okay, so this second angle that I'm looking at is all the way around to there. So that's going to be pi minus pi by 6, which is going to give me 5 pi by 6. Okay, now let's have a look at my range of values. My interval is 0 for x is 0 and 3 pi by 2. So if I write out the equivalent interval for 2x, which is what I've got here, okay, then that's going to be between 0 and 3 pi. So I need to get some more answers. How do I get some more answers? Well, I take these answers and I add 2 pi to them because that always gives me another set of answers. So if I do pi by 6, so let's write it out. If I do pi by 6 plus 2 pi, okay, that gives me 13 pi by 6. Use your calculator if we're not very good at fractions. And I also do my 5 pi by 6 plus 2 pi. Again, use your calculator if you need to, and that gives me 17 pi by 6. So to get my final answers for x, what I'm going to do is take each of my answers, which I've got 1, 2, 3, 4. I'm going to take each of those and divide them by 2. So my final answers, leave them in exact form. Pi by 12, 5 pi by 12, 13 pi by 12, and 17 pi by 12. And you can always, because they are exact answers, you can take them and sub them back into here. That would be a very useful check to do in the exam, just to make sure you've not made any errors in your calculations. You can sub them back and you will get exactly 2 because they are exact values. Okay, so that's worth 6 marks. So make sure you know how to do things like that. Okay, let's have a look at all of the things we need to do within our differentiation chapter. There's an awful lot of things. Get onto some interesting stuff next in the next few lessons. Very useful chain rule, product rule, quotient rule. But what we're going to have a look at today is differentiating exponentials and logs. Now, we've already done a little bit of differentiating exponentials and logs. Do you remember in year 12, one of the last topics that we did in chapter 14 was about exponentials and logarithms, and we worked out that if you've got y equals e to the kx, then what you do to differentiate that is you leave the e to the kx the same, and then you just times by k. So you remember when we looked at, for example, just the function y equals e to the x, if I do dy dx, I get e to the x. Do you remember when we were talking about this special letter e and its value? Remember, e is approximately equal to 2.718, that it's a special value such that the derivative or the gradient of the graph is the same value as the value of the function itself. Remember, that's what's special about it, and that's how things grow and decay within nature. Okay, so applying the rule that we've got up here, so make sure you've got that written down, put a box around it or highlight it in your notes. Let's do this second one. Also, thing to say, you're going to be doing lots of questions where you've got a function y equals or f of x equals. Please do write y equals and then write dy dx equals. Don't just put another equal sign, because that's just not the case. So for that one, I will get e to the 7x, and I will also get a 7. Notice, important thing to remember, you mustn't change the argument. That must stay the same. Okay? And then the last one here, when we've got separate terms added together, you remember with differentiation, you just differentiate them individually. Oh, we've got a 3x to the 4 here. Bring down the power, reduce the power by 1, 12x cubed. And then we've got an exponential one here. So e to the 4x would give me 4e to the 4x. I've already got a 4, so that's going to give me 16e to the 4x again. Be careful, remember, this power stays the same, do not change it. That's a common mistake that you can make if you're not careful. Okay, so that covers really differentiating your exponential functions. So what about logs then? We need to be able to differentiate ln x. Okay, and we don't know how to do it at the moment, so let's make use of some things that we do know. If y is equal to ln x, we know from the work that we've done on logs, the equivalent exponential form of that is x equals e to the power y. Just remind yourself, when you have ln, remember ln is log to the base e, and by our definitions of logs, okay, it is e, what power do I raise e to, okay, to get this x, and the answer is the y, so it's e to the y equals x. Now I can differentiate this, because it's x equals a function of y. When I differentiate, I get dx dy. It's just the letters are changed round, but it's exactly the same as what we've already done. We know if I differentiate e to the y, I get e to the y. Now my original function is y equals, so I want to find dy dx. Well, have a look at this that I've got here. Dx dy is the same as 1 over dy dx. So I can flip this side upside down, and I can flip this side upside down as well. Okay, then here comes the clever part. Dy dx equals 1 over, let's make use of this, e to the y is equal to x, so dy dx equals 1 over x. Okay, so when you differentiate ln x, you get 1 over x, and that's where it comes from. Okay, now we quite often, make sure you've got that written down, we quite often want to differentiate slightly more complicated things. It might not just be ln of x, it might be ln of some function of x. Okay, so if that's the case, then dy dx is equal to f dash x, so the derivative of the thing that's here is on the top, and the function f of x there is on the bottom. Now this comes from using the chain rule, okay, and we're going to do the chain rule next lesson, so it will become clearer why that is the case next lesson. Okay, so if y is ln of f of x, then dy dx is equal to the derivative of the f of x, okay, divided by the f of x. Right, and this is something that you do need to learn. These aren't given to you in the formula book at all, so you do need to actually learn these. Okay, so let's apply them to these examples here. If y equals ln of x, find dy dx. Well, we've just done that on the previous slide, but let's make sure that using this more general rule here, we do get the same thing. The rule is, whatever the function is here, differentiate it and put it on the top. Well, I get a 1. Put that function itself on the bottom, so I get 1 over x, which is what I showed you on the previous slide. Ln of x goes to 1 over x. Let's do this more complicated one then. Okay, so remember what the rule is. This is my f of x here, so I differentiate it and I put it on the top. If I differentiate 3x, I get 3, and I put the function itself on the bottom. Now, look what happens. The 3's cancel and I get 1 over x. That's interesting. So the derivative of ln of 3x is exactly the same as the derivative of ln of x. Why is that then? Well, let's see why. Let's use our log laws. Ln 3x, do you remember our log laws? If we've got something multiplied together, I can split it as ln 3 plus ln x. Do you remember that? That's one of our log laws. Now, when I differentiate, okay, if I differentiate this ln 3x and I split it in this way, ln 3 is a constant, so that goes to 0, and ln x gives me the 1 over x. So you can you see how those 3's cancel, because you can split it using your log laws if you want to. Okay. Right, let's do this final one then. Bit more complicated. Remember what the rule is. This is equivalent to my f of x. So the rule is, if I'm differentiating ln of something, I put the derivative on the top, differentiate that, I get 6x, and the 7 disappears. Derivative on the top, function on the bottom. Okay, might look complicated, but we just leave it like that. Okay, happy enough with those. Right, so we can now differentiate e to the something times x, and we can also differentiate ln of f of x. This is quite important, all this stuff, because we will use this a lot later on to integrate functions that look like this. Functions that look like this, when you integrate them, go back to lns, so just hold that thought. Right. So far, we can only differentiate e to the power something. Now, we may get functions that don't have e as the base. We might get a function that looks like that. Now, we need to be able to differentiate that. Now, here's the result. So if y is equal to a to the x, show that dy dx is equal to this. So this is the result. This is what you'll need to remember. It's a to the x, but then we've got this extra ln a. But why is that the case? And you may well be asked to prove this. All right, so make sure you understand the steps I'm doing here. So we start with y equals a to the x. Okay, now what I can do with this is, because I know how to differentiate, okay, e to the power something, okay, what I can do is I can write this as e to the power something. So what we need to remember for that is I write it as e. Remember, if you do e to the ln of something, okay, then the e to the power lns cancel out and you just end up with that something that you've got there. Okay, so happy with that. Y equals e to the a to the x is equivalent to y equals e to the power ln a to the x. Now let's use our log laws. We've got a to the power x, so I can bring down the power to the front and I get x ln a. Okay, so I've used my log laws. Remember, you have ln a to the power b equals b ln a. Remember, you can effectively bring the power down at the front. So that's what I've used for my log laws. Now, we can differentiate this because this is e to the power. This here is a constant. So that's exactly the same as, say, having e to the 2x. So when we differentiate, remember what we do? If we've got e to the 2x, it would be 2e to the 2x. We've got e to the x ln a, so it's equal to ln a times e to the same thing. Okay, so remember ln A is a constant, so then that can come down at the front. Okay, now let's resort this bit out like we did to start with there. So I can again use my log law in reverse, okay, to write that as e to the ln A to the x. The e to the power ln's cancel out, they are the inverse of each other, so I end up with ln A times A to the x, which is the thing that I want to prove. It's just written the other way around. Okay, so you may be asked to prove that. All right, so make sure you're happy with doing that. Remember, we introduce e to the power because I know how to differentiate that and I'm allowed to use that fact. And also that's a result that we need to remember as well. Okay, so let's do an example of that then. So here's my result up at the top that I need to remember. So if y equals 3 to the x, find dy dx. Well, dy dx is equal to, like with your exponentials, just write down the 3 to the x, leave it exactly the same, but the extra bit I need to do here is I need to times it by ln 3. Okay, so you can either put a little dot means times here, or you can put it in a bracket. It's up to you, as long as it's clear that it's that times that. Nice and easy. Okay, slightly more general form here. We might get a to the power kx, so we might get something like 2 to the power 3x. What's the difference there? Notice we still get the fact that you write, this down exactly the same here. The only difference, instead of writing just a ln A, you get a k ln A. Now this is actually one of the questions in the exercise I'm setting you to prove this. So when you get onto that question, just follow a similar approach to what we did on the previous slide, okay, and you'll get the result there. So let's make use of that. So y equals 3 to the power 2x. Now what I generally do when I'm differentiating these is the first thing I will do is write down my 3 to the 2x. That stays unchanged. Remember, I'm not changing the power. What do I times it by? Well, I know it's to do with ln 3, which is the base, but because I've got the 2 as the power, it's 2 ln 3. Okay, are you happy with that? Make sure, really important, do not change this power, okay? You write down that exactly the same. And I do find if you write that down first, then it avoids mistakes. So for this one, I'm going to write my function down again. It's not changed. What am I going to times it by? I know the ln is always the base, okay, but I'm timesing by 5, so I get 5 ln 4. Okay? Right, really nice complicated one to finish with here. Now we're going to have to use some of our skills to do with index laws to sort this one out first. Now what you'll notice, hopefully, if you're looking at this and you're thinking hard, the base numbers, at the moment they are different bases. If I could make them all the same base, that would simplify my expression there. So hopefully you have noticed that this 4 and this 8, I can change both of those into powers of 2. Okay, 4 is 2 squared. Okay, and they'll always give you numbers that you can do this to. And 8 is 2 cubed. Okay, remember doing some of these when we were doing index laws. So 2 to the 6x plus power to a power, times them together, 2 to the 4x. Again, power to a power over 2 to the 3x. Still need to simplify this. So what I do is I split it into separate bits. So I've got a 2 to the 6x over 2 to the 3x plus a 2 to the 4x over 2 to the 3x. You know, with your index laws, when you divide the same something with the same base, you subtract the powers. So you end up with 2 to the 3x for that one and 2 to the x for that one. I'm now ready to differentiate. Okay, so let's differentiate dy dx. Remember our rules. Write it down exactly the same, 2 to the 3x. What do I times by? 3 ln 2. Okay, the 2 to the x bit, sorry, that just ran out of room a little bit there, so I write underneath. 2 to the x goes to, write the 2 to the x, leave it the same, okay. What do I times by? Just a ln 2. Okay, so unless it's to show that, that is a perfectly good answer to just leave it like that. Okay, so hopefully you're happy with that. We're just going to finish off with just a couple more examples here that pulls everything together. So for part A, what I'd like you to do, maybe pause this, have a go at these, see if you've understood what I've done. Okay, right, let's see if you got them right then for part A. My first bit, e to the 3x, remember what you do, you write down the e to the 3x and it's just times by a 3. Okay, 2 to the power 3x, write down the 2 to the power 3x. What do you times by? 3 ln 2. Did you all get that right? Hopefully you did. Okay, part B then. So y equals ln x cubed plus ln 7x. Remember, when you differentiate ln, what you do is you look at the ln of something, you differentiate that something and you put it on the top, and then you put the something on the bottom. The something is the f of x plus ln of 7x. Again, differentiate 7x, you get 7 and put the 7x on the bottom. These will simplify and you are expected to simplify them, so make sure you do. X's cancel and you end up with 3 over x. Okay, 7's cancel, you get 1 over x. And actually, how nice is that? Those can collect together to give you 4 over x, so you would be expected to do that. Okay, now, y is a fraction, that's called a quotient. At the moment, we haven't done the quotient rule. We will do the quotient rule. Okay, so all we can do for this at the moment, hopefully what you thought was split it into 2. So I've got 2 over 4 e to the 3x minus 3 e to the 7x over 4 e to the 3x. So I've only got a single term on the bottom, so I can split it into 2 separate bits. Let's just simplify that a little bit, okay? Because remember, I want e to a power so that I can differentiate it. Well, that gives me a half. 1 over e to the 3x, e to the minus 3x. Happy with that? Minus 3/4. Remember, don't move the numbers around. E to the 7x divided by e to the 3x gives me e to the 4x. Okay, hopefully you managed to do that. Now I'm into differentiation. E's are really easy to differentiate. I leave the e to the minus 3x stays the same, but I times by minus 3, remember? So I get minus 3 over 2 e to the minus 3x. Again, the e to the 4x stays the same, but I times by 4, so I get minus 3 e to the 4x. Do not change, remember, do not change these. They stay the same. And that's our final answer. Okay, all done. Right, over to you. There are quite a few questions here. I think it took me just over 3 slides of work, but you need to do them. You really do need to work through and get these skills into your brains, because you will go on and use these in subsequent places in year 13. So questions 1 to 12, all parts. It is a lot of questions, so I would like you to submit, but I would only like you to submit answers to 9, 10, 11 and 12. There are some of your more exam style questions, okay? So I set up the assignment on Teams for that, and I'd like you to submit your worked answers for those, okay, by Thursday, 11th of June, so I can get them marked on Friday and then talk to you about them in our Teams lesson. Okay, if any of that was unclear, please do go back and have another look at it. Otherwise, good luck with the questions.